Section: Introduction. In this section, we discuss contrastive image text (CIT) models like CLIP, SigLIP, and Align, which have shown exceptional performance in high-level vision language tasks. These models excel in applications such as retrieving images from text, zero-shot classification, and serving as key components in vision and language systems. Their success is largely due to their ability to utilize large datasets to create a shared space where similar image and text concepts are close together. However, we recognize that existing CIT models have significant limitations. While they effectively capture high-level semantics, they often struggle with fine-grained visual tasks, such as spatial reasoning. This is because their training data and objectives do not emphasize precise spatial understanding or provide the detailed annotations needed for distinguishing similar objects. Consequently, tasks that require subtle visual comprehension, like multi-view reasoning and object localization, are more challenging than high-level tasks. To address these issues, we introduce TULIP, towards Unified Language Image Pretraining, an open-source alternative to current CIT models. TULIP aims to improve the learning of general visual features while retaining the language grounding strengths of existing methods. We tackle two main challenges: representing detailed spatial information and capturing nuanced visual details. To achieve this, we use patch-level global and local multi-crop augmentations and objectives, inspired by techniques like IBOT and Dino. Additionally, we introduce a reconstruction objective to maintain high-frequency local visual details that are often overlooked by current contrastive objectives. We also propose a generative data augmentation strategy using diffusion models to create challenging hard negatives that enhance fine-grained semantic grounding. We evaluate TULIP against existing CIT models, such as OpenAI's CLIP and SigLIP2, across a variety of vision-centric tasks. Our results show that TULIP outperforms state-of-the-art models in all benchmarks, including zero-shot classification and text-based image retrieval. Furthermore, we assess TULIP's robustness in vision language tasks by using it as a visual encoder in a LLAVA-style model, achieving significant improvements in vision-centric tasks without compromising performance on language tasks. We also evaluate reasoning and perceptual skills using benchmarks like Blink and Winneground, where TULIP shows notable improvements over existing models. In summary, our main contributions include: I. Introducing TULIP to enhance fine-grained visual representation while maintaining language grounding. E. Incorporating multi-crop augmentations for better spatial awareness. E. Introducing a reconstruction objective for high-frequency details. IV. Proposing a generative data augmentation strategy. And V. Establishing new state-of-the-art performance across various vision and vision language benchmarks. Section Summary. In this section, we discuss the limitations of existing contrastive image text (CIT) models, which excel in high-level tasks but struggle with fine-grained visual understanding and spatial reasoning. We introduce TULIP, a new framework that enhances the encoding of detailed spatial information and local visual details, demonstrating state-of-the-art performance across various vision and vision language benchmarks. Section: TULIP. In this section, we introduce TULIP, a powerful model for image-text contrastive learning that combines various approaches to enhance how we learn representations. Our key insight is that images and their captions offer different perspectives on the same reality. For instance, a photo of a cat on a bench paired with the caption, "A cat is sitting on a bench," reflects two views of the same situation. Contrastive learning helps us align these views in an unsupervised manner by mapping them to the same point in a shared representation space. Therefore, defining what counts as a valid view of the content is crucial for our approach. We first explain how TULIP utilizes images and text to create different views in the contrastive learning process. Then, we describe how TULIP generates diverse views from reality using generative augmentations and how it employs reconstruction laws to strengthen the learning of robust representations. To diversify contrastive views, we note that previous methods mainly contrasted an image with its corresponding text or an augmented version of itself. We unify these methods by considering every transformation of an image or text as a valid view of the underlying content, which we incorporate into our contrastive learning framework. Our contrastive learning loss includes three main components: image-text, image-image, and text-text contrastive learning. For the text encoding in TULIP, we do not use an exponential moving average teacher since there is no clear structure in the views. Instead, we utilize a text encoder with directly tied weights, specifically SigLIP's language encoder. We also introduce JCO, a method for generating diverse contrastive views. Existing models often rely on fixed sets of views, which can limit the learning of semantic features. We recognize that the choice of views significantly affects the model's performance. JCO leverages large generative models to create semantically equivalent and visually similar augmentations during training. It automatically modifies both images and text to produce positive and negative pairs for our contrastive components. Positive views are those that maintain the same semantics but are presented differently, while negative views are semantically distinct yet share visual characteristics. Since paired data is often scarce, JCO uses generative modeling to create these views from existing image-text pairs. The overall process of JCO involves two main components: language augmentation and image augmentation. Section Summary. In this section, we introduce TULIP, a contrastive learning model that integrates various image and text views to enhance representation learning, utilizing generative augmentations to create semantically relevant positive and negative pairs. We also discuss how our approach unifies different contrastive learning methods and employs reconstruction loss for more robust representations. Section Main. In this section, we discuss image augmentation. To enhance our images, we fine-tune an instruction-based image editing model using soft prompting to create both positive and negative augmentations. Specifically, for our image editing model, we learn embeddings for positive and negative views. We utilize various sources for image augmentation, including traditional methods like color adjustments, flipping, cropping, and blurring, as well as additional techniques. For positive training, we incorporate video data, considering frames that are closely related in time as semantically identical, and we also use multi-view data of the same object. For negative training, we rely on large datasets that capture semantic image edits, as these edits reflect the image's semantic changes. Our approach, TULIP, allows us to take an image and its paired text to generate both positive and negative augmented views. We can use these views for training either during the training process or by caching them for later use. In contrastive learning, our model takes an input, image or text, and produces both an augmented positive view and an augmented negative view. We define sets of indices for negative views and establish relationships between the views based on whether they are negative pairs. Next, we address regularization with reconstruction. While using diverse contrastive views through generative augmentation can enhance our model's performance on fine-grained semantics, it can also create hidden invariance, where different augmentations map to the same point. This invariance can hinder performance on tasks requiring high visual fidelity, such as color identification or depth estimation. To counter this, we introduce a pixel-level reconstruction objective to our model's latent vector. We assume that if our model can reconstruct the image from the latent space, it will capture essential visual details while maintaining semantic invariance. For image reconstruction, we use a masked autoencoder model, which helps the model focus on shape and detailed information rather than just global patterns. For text reconstruction, we employ a causal decoder with the text embedding as the starting point. The loss from this regularization combines the reconstruction losses for both images and texts, with weights to balance them. To minimize computational costs, we compute reconstruction in both modalities but only use the latent vectors from one modality during each training pass. For instance, in image-image contrastive learning, we calculate the reconstruction loss from one image embedding, and later, in image-text contrastive learning, we compute the text reconstruction loss from the existing image embedding. Section Summary. In this section, we describe our approach to image augmentation using a fine-tuned generative model that creates both positive and negative views of images through various traditional and novel methods, including video and multi-view data. We also introduce a pixel-level reconstruction objective to balance high-frequency visual details with semantic representation, ensuring our model retains essential visual information while learning from contrastive views. Section: Experiments and Results. In this section, we discuss our experimental design, training process, and results for TULIP. For optimization, we utilize the Atom Optimizer with a learning rate of 0.001, weight decay of 0.001, and apply gradient clipping to a norm of 2. We set our batch size to 49,152 and train our models using up to 32A100 GPS over several days. Our initial experiments assess the quality of the image text representations learned by TULIP. We explore zero-shot classification, text-to-image and image-to-text retrieval, and linear probing for fine-grained classification datasets. To evaluate TULIP's compositional reasoning abilities, we conduct further tests on the Winogrand dataset. The results clearly show that TULIP excels in visual reasoning compared to existing vision and language models. One of our motivations for developing robust vision and language models is their potential as feature encoders for large-scale multimodal models like LLAVA. We fine-tune LLAMA 3.211b using a set of visual encoders with LLAVA mixture data and evaluate performance on various benchmarks. These include the BLINK benchmark, which consists of 14 perceptual tasks, the MMVP benchmark for visual capabilities, and LLAVA bench for conversational and reasoning tasks. Our results on the BLINK dataset indicate that TULIP performs well across all problem types, particularly excelling in vision-driven tasks compared to base methods, outperforming GPT-4o in spatial reasoning and localization. The results on MMVP and LLAVA show that while DINOV2 fine-tuned models excel in MMVP, they struggle with language tasks. In contrast, CLIP-style models perform better in language tasks but have difficulty with visual perception. TULIP combines the strengths of both, outperforming DINOV2 and SigLIP in their best tasks. In our ablation studies, we observed the performance of TULIP with various components removed. The largest improvements in MMVP come from image-image contrastive learning and our base data training pipeline. Reconstruction further enhances performance on both the vision and LLAVA benchmarks. Notably, the LLAVA benchmark performance appears to be saturated, indicating that further improvements may require enhancements in the large language model or visual adapter.